All right, so we're going to start talking about transformations. It's a conversation I'm sure you've had in your other math classes before, and we want to revisit it here. It shows up a lot on ISTEP and different standardized testing, so we definitely wanted to make sure we went through this. Different types of transformations. We're talking about taking a figure and either translating it, reflecting it, rotating it, dilating it, or doing a combination of those things. We'll talk a little bit about symmetry too, both line and rotational symmetry, and we'll talk about what that means. So, again, your transformations are listed there. We're talking about, first, translation. Sorry about that. Translation means we're going to slide it so that the figure, if it starts there, ends up over here. Okay? We're just literally picking it up and moving it. And there are different ways that we can get to those types of movements. Right? So by the time we're done here, we should be able to perform a translation. We're not going to worry about compositions yet, but here just with the translation. So some vocab for you first. A translation, like I said, moves every point of a figure the same distance in the same direction. So we're picking it up, sliding it over, and setting it back down. Before you move a figure in a transformation, it's called a pre-image. That's the original figure. The image is what you get after the transformation. So whether it's translation or reflection or rotation, you start with a pre-image and then you get an image. And an isometry, which most of these transformations will be, actually all of them except for dilation, is a transformation that preserves length and angle measurements. So whatever we have when we begin should be what we end up with after our transformation. Okay? All right. So with translations, like I said, we're picking up points and simply moving them. What we need is some sort of coordinate rule or translation rule, right? And that's what this guy right here is for. The x comma y translates to x plus 3 comma y minus 1. And all that says is that we're going to move, obviously x-axis is in the horizontal direction, so we're going to move everything to the right 3, and then the y direction is the vertical direction, so we're going to move everybody down 1. So we start with the pre-image, so we want to graph A, B, C, and D. And we get this quadrilateral. I'm having a hard time here making these straight to where they make enough sense. But anyway, so there's your quadrilateral, which hopefully you recognize as a trapezoid since A, B, and C, D are parallel. But anyway, we're going to move all the points right 3, down 1, and we'll get our image. So A, we go over 1, 2, 3, down 1. So A prime, which is what we how we denote the images. After the transformation, we take the vertices and just give them a prime or an apostrophe read as prime to let us know that the prime is the image, where the regular notation is your pre-image. Sorry about that again. So we go over 1, 2, 3, down 1 for the B. So B prime is there. 1, 2, 3, down 1 from C. C prime is there. 2, 3, down 1. D prime is there. And our new trapezoid sits there. Okay? That's it. That's literally how we do that. Very straightforward, right? All right, so you take a shot at this triangle RST. So R, which is at 2, 2, S, which is at 5, 2, and T, which is at 3, 5. So take that triangle, translate it using this translation rule. So x plus 1, y plus 2. You can stop the video, start it back up, and make sure you're doing okay. Right. So R prime is going to go, we're going to get that by going right 1, up to, so R prime will be right there. S prime will be right 1 up to, so right here. And then T prime will be right 1 up to, so T prime will be right there. Now, if you did not have a graph to go off of, right, so there's your new triangle where it sits, R prime, T prime, S prime. But we do have the coordinates, and so we can take this rule of +1 and +2 and just add 1 to the x, add 2 to the y for every one of these points, and that would create new coordinates for R prime. So 2 plus 1 is 3, 2 plus 2 is 4. S prime, 5 plus 1 is 6, 2 plus 2 is 4. And then T prime, 3 plus 1 is 4, 5 plus 2 is 7. So we could just get the coordinates that way and then plot the new coordinates. Either way, doesn't make any difference. Okay, that's where it should be. Now, think of it going a little bit different here. So let's say that the image from this translation rule results in a segment P prime, Q prime, where the endpoints are P prime -3, 4 and Q prime at 2, 1. We want to find the coordinates of the pre-image. So we performed some translation and got our points to end up there. How do we go back to the pre-image? Well, hopefully you're thinking, just go backwards, right? Instead of adding 4, subtracting 7, go the opposite direction, subtract 4, add 7 to each of our coordinates, and that'll get you to your pre-image. Just go the other way. That's exactly right. So P is going to end up at -7, 11, and Q would sit at -2, 8. So that's where our pre-image would be. Okay? All right? Next, write a translation rule. And then it says, verify that the transformation is an isometry. Okay? So, how do we go from ABC, triangle ABC, to triangle A prime, B prime, C prime? And so our translation rule always starts with x, y moving to, and then we got to write in our rule. We'll just go from A. Go from A to A prime. How do we get there? When we go to the left, 1, 2, 3, 4. So left 4 would mean we take each x coordinate and subtract 4. And then we have to go up 1. That means we take each y coordinate and add 1 to it. And that should get us all of our points. Now, in terms of verifying that this transformation is an isometry, that means that we've got to make sure that all the side lengths and all the angle measures are the same. Well, side lengths are not a big deal. We're talking about just finding length in the coordinate plane. So we could do distance formula, or in the case of AC and CB, we could just count grid lines since those are horizontal and vertical lines. So the length of BC is going to be 3, the length of AC is going to be 2. And then we see that a vertical and horizontal line meet, so that means that this is going to make a right triangle, so I could just do Pythagorean theorem to find the length of AB, which will give you 13. Then I can come over to our image and make sure that all of the corresponding lengths are the same. So C prime, B prime is 1, 2, 3. A prime to C prime is 2. And so if we were to do Pythagorean theorem, we get the exact same thing here as we did there, which is 13. So the lengths have been maintained. This also helps us talk about the fact that the angles have been maintained as well, right? How do you say, well, these two triangles are congruent by side, 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 right? And since the two triangles are congruent, then corresponding parts of congruent triangles are congruent as well. So that means that each of the corresponding angles have to be congruent as well. So if you had to verify that, you'd want to show finding all those side lengths and then talk about the fact that the two triangles are congruent by side, 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 or whatever method. And that means the angles have to be congruent because of CP/CTC. Okay? All right. Next one says write a rule to translate triangle A prime, B prime, C prime back to triangle ABC. So you take a shot at that. Write the rule that takes the pre-image, takes the image and maps it onto the pre-image. Stop the video, start it back up, and give it a shot. Okay, what'd you come up with? Well, remember, we're going from the image to the pre-image. So from A prime over to A. And to get there, we had to go right 1, 2, 3, 4. So we had to go x plus 4, and then down 1, so y minus 1. And that's our rule. Okay? All right, hopefully that makes enough sense. Now, that translating rule helps you understand how to translate our figures through the coordinate plane. We can also use vectors. Remember this guy from Despicable Me, right? Vector, he always committed his crimes with direction and magnitude. That's what a vector does here for us. Vectors are used heavily in things like physics and engineering and things like that. But a vector is a quantity that is measured by an arrow, and the arrow shows direction and magnitude. It's the direction in which we're going to translate something and the force in which we're going to translate it, or the magnitude. So the arrow is drawn from one point to another. The first point is called the initial point. That's the starting point of the vector. And then the ending point is the terminal point. Now, when you draw this in, it looks like a ray. The difference between this and a ray is that a vector ends. It has a terminal point, whereas an array it does not. And then when you name it, it's a little bit different as well. So for this particular vector, we always start with the starting point and then end with the terminal point. So we would call this vector AB, and we use kind of a half ray symbol above as our way of naming this vector. Okay? So that's what vectors are. And vectors, like I said, have direction and magnitude. One way that we can express a vector is in what's called component form. Component form combines the horizontal and the vertical components of the vector. So if we go back to this, obviously this vector is moving to the right and up. So it has a horizontal and a vertical direction going on at the same time. Component form breaks those down and just sort of separates out the horizontal and vertical components. Obviously, a horizontal component means how is it going left and right. And then the vertical component is how it's moving up and down. Okay? When we write that, we use these inequality symbols as grouping symbols, and then we'll put the horizontal first and then the vertical component second to let you know how is it moving in the x direction, how is it moving in the y direction. Okay? So, for example, this. Name the vector and then write its component form. Well, this is obviously vector BC. And its component form would be horizontal direction first. So from B to C, we have to go over 1, 2, 3, 4, 5, 6, 7, 8, 9. And then the vertical component would be down 2. So that would be its component form, 9, negative 2. Okay? Same thing with this guy. We're still going to call it vector ST because S is the initial point. T is the terminal point. Its component form would be horizontal component first. So we are going left. 1, 2, 3, 4, 5, 6, 7, 8. Left 8 means we're going negative 8. And it doesn't have a horizontal component, a vertical component because it doesn't go up and down at all. So just make it 0. Okay? So you try. Name the vector and write its component form here. I'll give you a second. You can stop the video. Okay? So what did you come up with? Vector RS with component form 1, 2, 3, 4, 5. So 5, 0, right? because it doesn't go up and down at all. How about this guy? So vector, tx, and it has component form 0, 3, right? One more. So vector bk and the component form will be -5, 2. Let us know we're moving left 5 up 2. Okay? All right. Now, we can translate an entire shape the same way. We can take triangle A, which is at 0, 3, B, which is at 2, 4, and C, which is at 1, 0. And now we're going to translate it with vector, with component form 5, -1. That means that we want to move right 5 and down 1. So our terminal point for our vectors would be here, here, and here. So this would be B prime, A prime, and C prime. So it just tells us how it moves. Okay? We could do the same thing with the coordinates here that we did for the translating rule. Since the component forms are 5, -1, we can always add 5, subtract 1 to each of our points. And we'll get to those points there. Okay? All right. You try this one, right? Come up with the coordinates for L prime, M prime, and N prime. You can stop the video, start it back up, and make sure you're right. Okay, so the component form of our vector is -2, 6. That means you're just going to subtract 2, add 6 to each of our points. So 0, 8 for L prime, 3, 9 for M prime, and 7, 7 for N prime. And that'll give us our new triangle. Okay? All right. Next one, and I don't believe this is in your notes, but navigation, right? Vectors are used quite a bit in navigation because it has that vertical and horizontal component. There usually are degree measures associated with vectors as well, just a different way of expressing it. But we can use this to come up with some vectors as well. So, first of all, the boat starting at point A, travels to B, gets hit by a storm, gets pushed off course to C, is trying to get to D, right? So if you want to write the component form of vector AB, well, just how far is it moving from A to B in the vertical and horizontal directions? Horizontal directions is going from 0 to 12, which means it's moved positive 12. And in the the vertical direction, it moves from 0 to 4, so it's gone 4. BC. Well, from B, it went from 12, 4 to C, which is 16, 2, which means that the horizontal component still increased by 4, so make that a 4, but the vertical component decreased by 2. So the vector from B to C would have to be 4, -2. And then it says, write the component form of the vector that describes the straight line path from the boat's current position C to its intended destination D. So here to there. You can just find the differences again in the X and Y coordinates. So we have to add 2 from C to D and then add 3 from C to D. So that would be the component form of that vector. Okay? And last but not least, in example 5, suppose there's no storm. Write the component form of the vector that describes the straight path from the boat's starting point A to its final destination, D. So now we want to go from A to D, and the component form of that vector would just be 18, 5. Okay? Which you can get from the graph, or you can just add up the horizontal components of all the other vectors. 12 plus 4 plus 2 is 18. And then add up all the vertical components of the other vectors. 4 plus negative 2, which is 2. 2 plus 3 is 5. And you get to 18, 5. All right? So there you go. All right. Now let's move into symmetry and dilations. Symmetry. A figure has line symmetry if we can draw a line in a plane and basically be able to fold that shape over onto itself and map it right back onto itself. That line is called the line of reflection. Okay? Or it could have rotational symmetry, which means that we can rotate the figure about a certain degree measure and get to map back onto itself from there. That degree measure of the rotation has to be 180 degrees or less. Right? So anything above 180 degrees no longer counts as rotational symmetry. It's kind of like cheating. Every shape you can turn it 360 degrees and map it back onto itself, so that doesn't really count. We need to be 180 degrees or less to have rotational symmetry. Right? So, for example, there's 3 hexagons here, and to come up with line symmetry or rotational symmetry on your own, on its own, you kind of have to just use your imagination a little bit. For this hexagon right here in A, I know I can draw a vertical line through it and get it to fold over onto itself, and I can draw a horizontal line. So there's 2 lines of symmetry. There's not really anywhere else I can go with this. I can't go in a diagonal, because if you fold it on the diagonal, it's not going to map onto itself. And I can't go from mid-side to mid-side, opposite side, for the same reason. So for this guy, it's only going to have 2 lines of symmetry. Like I said, this one and this one. In more of a regular hexagon, we could go here, here, or through any of the diagonals, and through any of the sides. Right? So this guy is going to have 6 lines of symmetry. And then this last guy, again, just kind of using your imagination, if I draw a line through it this way, I can fold it onto itself. So this is going to have 1 line of symmetry. Okay? And so like I said, you have to just sort of use your imagination a little bit. So here's some practice for you. Go through and come up with how many lines of symmetry are in these shapes. In the case of the flower, close enough, because it's a flower, we can go through there and then through in between the petals. But then pretty close and close enough, we could actually go through pieces of those petals and still get this guy to map onto itself. It wouldn't be exact, but it'd be awfully close. So this guy ends up having 8 lines of symmetry. The starfish, you can go through each of the legs. So this guy's got 5 lines of symmetry. And then the ram here, you can just kind of split it down its head. So this guy has 1 line of symmetry. And then over here, draw a hexagon that doesn't have any lines of symmetry. Well, that'd be a pentagon. So probably something like that. But you can come up with your own shape that shouldn't have any lines. Just kind of randomly draw 6 sides. Right? Okay. Now, rotational symmetry means that we can rotate this thing around to map it back onto itself. And 360 doesn't count. Anything more than 180 doesn't count. So for that parallelogram that you see there that I can't take this vertex and map it to that one. But I can take this vertex and map it onto that one. And so this guy's going to have 180 degree rotational symmetry. And that's it. We don't go any more than 180. This regular octagon, I could take this side and take this shape and turn it at an angle and get it to map onto that side, and it would map back onto itself, which is 45 degrees. That's a 45-degree turn. It's not quite 90. It's in between 90 and 0. I could take this side and map it onto that side, so that would be your 90-degree turn. I could take the top side and map it onto this one, which, if you start following some pattern recognition, would be a 135-degree turn. Then I can take that side and map it onto this one, which is going to give you a 180-degree turn. And that's where we stop. So wherever our initial rotational symmetry sits, we're going to continue to turn this thing around until we get to 180 and stop. Okay? A trapezoid. Well, think about it. I can't map that vertex onto that one, or simply onto that one. Just use your imagination, right? So this guy has no lines of symmetry. Now, that's just using your imagination. There is a connection between line symmetry and rotational symmetry. Excuse me. If you look at the parallelogram, it has line symmetry here and here. So it has two lines of symmetry. The regular octagon has a bunch, right? We can go vertical or horizontal. We can go through the opposite sides. We can go through all of the vertices, so the diagonals. So believe it or not, this guy's got 8. And the trapezoid does have one line of symmetry, even though it doesn't have rotational symmetry. So if you take a look, turning something all the way around back to itself is a 360-degree turn. Well, if you get 360 and divide it by 2, you get 180. If you take 360 and divide it by 8, you get 45. And if you take 360 and divide it by 1, you get 360, which doesn't count as a rotational symmetry. So the bottom line is, if you take your number of line symmetry and divide it into 360, that will tell you your first rotational symmetry, and then you can add that on each time after until you get to 180. Here's another way to come up with your rotational symmetry. Okay? All right. So try these. Come up with the rotational symmetry for these guys. You can stop the video, start it back up, and see if you're right. All right, what you got? Rhombus has just 180 degrees, right? If it helps, just 2 lines of symmetry. Octagon. This octagon has 90 degree and 180 degree rotational symmetry. If you turn it 90 degrees or 180, you can map it back onto itself. And it has 4 lines of symmetry to help you out. The right triangle has none, right? No lines of symmetry, and so no rotational symmetry. All right? Next example here, standardized testing, line of symmetry and rotational symmetry for the equilateral triangle at the right. Well, I think the line symmetry is a bit easier than the rotational symmetry here. You should be able to just draw a line through each of the vertices and get a line symmetry. And those are quick drawings. So there's 3, right? Since there are 3 lines of symmetry, divide 360 by 3 and you get 120. So that means it has 120 degree rotational symmetry. 3 lines of symmetry means the answer here is going to be B. Okay? All right. This next example. Describe the lines of symmetry and rotational symmetry of a non-equilateral isosceles triangle. A non-equilateral isosceles triangle would look something like this. Isosceles, but not equilateral, so not all 3 sides are the same. And so the only line of symmetry that you're going to have for this guy is coming right down through the middle, or an altitude, right? So its altitude is its line symmetry. But there's not going to be any rotational. Right? Because there's only one line of symmetry. 360 divided by 1 is 360. Okay, sorry about that. All right. So try going through this, right? Coming through your line symmetry and rotational symmetry for all the letters in the alphabet. And stop the video and start it back up to see how you did.